Okay, this is the second half of our rotation unit, and in this part we're looking at Chapter 12. And Chapter 12 deals with rolling and torque. We're not going to have a whole lot more new ideas in this chapter. We're mainly going to be applying what we've already learned. And rolling is an interesting case, and there are two ways to treat it. So you could have, if you've got a wheel rolling on flat ground, you could treat it as sliding plus rotation. That's the usual way we think about it. The center of mass is translating, and the wheel is rotating about the center of mass. So in this case, we'll usually take an energy approach. So we'd say the total kinetic energy of the wheel is 1/2 mv squared plus 1/2 I omega squared. But if the wheel's radius is r, then omega equals v over r, and so it would be 1/2 mv squared plus 1/2 I v squared over r squared. And that is the easiest thing to think about from a conceptual point of view. However, we'll find that it really doesn't work very well with a torque approach, which is typically more useful in physics problems. So that torque approach is to treat rotation, if you got your wheel on the ground here, as pure rotation about the contact point. So if you take a snapshot of the wheel, you notice that it's basically rotating about this point. And so if you look at all the points on the edge of the wheel, the top of the wheel is moving fast. The middle of the wheel is moving half as fast. That point is moving like that. The point on the edge right there is moving a bit downward and also forward a bit. That's moving like that. And basically, the whole thing can be viewed as a rotation about that point instantaneously. Of course, one moment later, the point of rotation has changed, but we're really going to take a snapshot approach to it. Now, if we do this, we have to use the parallel axis theorem, because we're rotating about a point that is not the center of mass. So if you know the moment of inertia of the wheel about the center of mass, which you usually do, now the moment of inertia about this point right here, by the parallel axis theorem, is I about the center of mass, plus the mass of the wheel times the radius squared, because the center of mass of any well-designed wheel is right at the axle. And if you're using a torque-based approach to a problem, this is typically what you'll do. Now, for the remainder of the video, we're going to look at the very interesting case of something rolling down a ramp. Now, we know how to handle something that slides down a frictionless ramp. We know that the forces acting on it are a normal force and the weight mg. And if we calculate this, we end up getting A equals g sine theta. However, let's say it's rolling. What makes it start rolling is, rather interestingly, the friction between the ramp and the edge of the wheel. If there were no friction, this wheel, instead of rolling down the ramp, would slide down the ramp. And so if we draw the forces on this, we have mg, which acts at the center of mass, we have a friction force back that way, and we have a normal force perpendicular. So for any particular object, rolling is actually going to be a little bit slower than sliding without friction. And one way, and to look at that from an energy perspective, if you have sliding, all of the initial potential energy turns into translational kinetic energy, but when there's rolling, some of the initial potential energy turns into rotational KE instead, which means that there's not as much translational kinetic energy, which in turn means a smaller speed. So really, either way you look at it, it's quite interesting. Now, we're going to work this problem with the force approach. I'd encourage you to work it through from an energy approach too. Make sure you get the same answer. I'm not going to do that in this video. But we've got a wheel, which we're going to treat as a solid disk of radius r, rolling down a ramp that's angled at 20 degrees, and I'll just call that theta for now. Now we want to find the speed at the bottom of the ramp, and to do that we're first going to use the torques and forces to find the acceleration of the wheel, and then we are going to use that and the kinematics to get the speed at the bottom of the ramp. So using the forces, we're going to draw an extended free body diagram for the wheel, and we'll say that, okay, there's a friction force like that, there's a normal force like so, and then from the center here, we have mg. I think you'll be able to see that this angle is equal to theta. I'll put it like that. And that therefore this angle is 180 degrees minus theta. Now what we'll do is we'll make our pivot point just like that. And so if we look at the sum of the torques about that pivot point, the normal force and the friction force produce no torque because they are acting right on the pivot. Whereas mg is acting a distance away from the pivot r, but the angle between it and the r vector is 180 degrees minus theta. Of course, if you know a little bit of trig, you know that sine of 180 minus theta is equal to the sine of theta. So we'll simplify that a bit. And we also know that the net torque equals the moment of inertia times alpha. And now here comes the algebra. Alpha equals A over R. If we look up on page 227, we find that the moment of inertia about the center of mass of a solid disk is 1/2 mr squared. And using the parallel axis theorem, we'll add a full mr squared to that to get the moment of inertia about a point on the rim. So the moment of inertia is 3/2 mr squared. So 3/2 mr squared times A over R equals mgr sine theta. And we find that all the masses and all the radii cancel out, and after some algebra we get A equals 2/3 g sine theta. Notice that that is slightly smaller than the acceleration g sine theta that you would get if it were just sliding without friction. And if you calculate it, you get 2.23 meters per second squared for the acceleration. And I'll make this a bit smaller, give myself some working space. Now we've got to find the speed. So now it just becomes a kinematics problem. We use the third kinematic equation. V naught is 0, we're looking for V. Delta x is 3 meters. And so when we plug in numbers, we'll get the speed at the bottom equals 3.66 meters per second. And that is how you do a torque-based approach to rolling. For a kinetic energy-based approach, you'd have the initial potential energy equals the final kinetic energy translational plus the final kinetic energy rotational. You should get the same answer. For tomorrow, I'm going to be checking questions 1 and 2. This is from chapter 12.